All right, so this is section 1.5. This is going to be video 2. We're going to do this real quick example here using a calculator. I think it's important that you know some of the functions of the calculator, and I can't assume that you know it all, but some things are going to be very useful in the future. While a lot of the course will be done without a calculator, it still is important you know how to use it. And then we'll get into some of our application problems. So if we have something like x plus e to the x equals 2, what you should notice is that you have a combination of a linear function and an exponential function being added together. So we can't use some of the same properties and some of the same things that we did in order to solve either exponentials or linear or polynomial type functions. So we're going to go ahead and plug this one into the calculator and see how this works. So I am going to be, whoops, I didn't need to pull all that up. Where is it? There it is. I'm going to be utilizing the TI-84. Specifically, it's a TI-84 Plus. And if you're using something else, I'm not going to be able to help you too much with that. But with the TI-84, this is pretty much how you'll do it. So you're going to want to plug in these things into your y equals screen, into your function screen. So you're going to hit the y equals button, which is in the upper left, and then you're going to type the x plus e to the x in. So the x button is the one that is directly next to the alpha button. It says x comma t comma theta comma n. So it'll be x, and then we're going to add e to the x. Now the e button is just above, it's in blue, it's just above where it says capital LN on the left-hand side, third button up from the bottom. So it'll be second e, and then you're going to type in x again. Okay, so that is your first function. So now we're going to hit enter, and it'll take us down to y2. Well, the right side of the equation is 2. So we're just going to literally type in y equals 2, which should be a horizontal line. And then we're going to graph this. Personally, when I graph a function, I always start off with a zoom 6. Zoom is the middle button in the very top. And 6 just gives you a standard 10 by 10 window. That way, if your calculator was in some other mode or something else was going on, it would be back to a standard window. So you should be able to see where the two of those things intersect. Now, this part right here is like, this is going to be like your best friend when it comes to these things. You're going to use the second trace. So you're going to push second, and then the trace button is up on the top row, fourth one over, which is actually going to be the calc feature, the in blue. So it's second trace, and we are simply looking for the intersection of these things. We want to see where the two things are equivalent. So we'll select 5, or you could scroll down and push enter. Now the calculator is asking you, are we on the first curve? Yes, you are on the first curve. So I'm just simply going to push enter to say yes. And then it jumped up. It's hard to tell, but you can see kind of jumped up to that horizontal line. It's asking you, are we on the second curve? So let's say yes. And then it's saying, do you want me to guess the solution? So we're going to say yes, because we are very close to where the intersection is. And there is your intersection. So x is approximately equal to 0.4428544. Depending on how many decimals something asks you to do, 2 or 3 decimals is usually perfectly fine. We're going to go 2 here. So we're just going to say x is approximately equal to 0.44. All right, so that's kind of one way you would use the calculator. Another way would be to take the original expression and subtract 2 from both sides. So we would get x plus e to the x minus 2 equals 0. So, okay, let's go back to the calculator. Y keeps pulling up that whole thing. I'm not trying to do that. We're going to go back to the y equals screen, and I am actually going to go down to y2 and just clear it. Go back up to y1, and what we did was we just subtracted 2 from both sides. And I'm going to graph that one. Again, zoom 6, but since it's already in a standard graph, it should work. So that's what it looks like. Now it's just one function because I've just made it one thing. So now what we're looking for is where that equals 0. Well, let's go back to second trace. And now we're not looking for an intersection. I mean, technically you are, but we're looking for the intersection with the x-axis, which is called the zeros, number 2. Now what this is asking me, is this the left bound? Am I bounding to the left of where I want the solution? That cursor you can see is clearly to the left-hand side of where the solution tends to cross. I'm going to move the cursor just a little bit so you can see it better. The solution looks like it crosses right in between the 0 and the 1, which we already know the solution should be there. So you can do this one way or another. You can either just say yes, because it's already to the left. You can move your cursor to the left or the right until it gets to the right spot. Personally, I think it's easier just to type in a value. So I know 0 is to the left of my solution, so I'm going to type in 0 as my left bound. And what you can see is it places that little arrow up there. I know 1 is to the right, but I'm going to pick something even further. I'm going to pick 2 for my right bound. And what you can see is those 2 arrows, move the cursor out of the way. The 2 arrows up there are bounding that that 0. That the arrows are saying, yes, I want my solution to be in between that. So now it's asking us, do we want it to guess? Yes, we do. And you can see that you get exactly the same answer. I'm not going to rewrite the answer, but 2 different ways to do the same problem. I'll let you figure out which way works best for you. All right, now we are going to move into our application-based problems. All right, in order to do this, we have to understand a little bit about exponential growth and decay, because that's what we're looking at basically here. So for exponential growth and decay, the basic form of this is the same. This is assuming that we experience what is called natural exponential growth or decay. Your formula basically is y equals c e to the kt power. And the pieces that you need to know are that c is your initial amount. Whatever it is we start off with, that's the initial value, the initial amount. K is what is called the constant of proportionality. Also might be called the growth rate. T, as you might expect, represents time. And then E is the number E. Y is what we're ultimately going to get for an answer. So those are the important pieces of information that you need to know for exponential growth and decay. Again, this is for if you are experiencing what is called natural growth or decay. Some of the most common applications of this are bacterial growth or half-life of an element or something like that. And that's pretty much what we're going to deal with here. So let's go ahead and look at an example. And I do apologize because this is going to be a little bit longer for everybody to kind of write out these problems. But let's assume that we have a function. So I'll call this example 1, where n of t is defined to be 100 e to the 0.045 t. And whatever this thing is, n is going to be measured in grams. N is the amount of grams. And of course, t is going to be time, and we're going to call that days in this case. So it'll be in days. So we're basically this is an equation that's going to measure the amount of grams that we have over a certain amount of time. So let's just kind of go step by step here. We'll take this in pieces. Let's say that we just want to figure out what the initial amount of bacteria is. Initial amount of bacteria. Well, the initial amount of bacteria, once again, is given where that C value is. That's right there. So the initial amount of bacteria is 100 grams. Okay, again, you should be able to look at that formula in the equation and figure that out pretty easily. Oops. For part B, what is the growth rate? What is the growth rate? And again, the growth rate is that that K value. So the growth rate, well, K itself is going to be 0.045, but that's not really the percentage. The growth rate as a percentage, of course, you know you have to multiply it by 100. So your growth rate is actually going to be 4.5%. And the important thing about that is if you were given the growth rate, say they tell you the growth rate is 4.5% and you want to write that in the equation, then you would know you have to divide that by 100 in order to write it as the appropriate decimal for the equation. All right, part C. This is where we're going to end up having to do some calculator work. What is the population? What is the population after 5 days? Well, if we want to know what the population after 5 days is, we are looking for n of 5. Oops, that's supposed to be in orange. There we go. Which means we are simply going to plug 5 in for t. And see what we get. So that, like I said, is going to be a calculator problem. So let's go ahead and bring the calculator back up. And we're just going to plug this into the calculator, clear out the previous graph that we were using. So that's going to be 100 e to the 0.045 times 5, all in the exponent, and we get an approximate value of 125.23. 125.23. So n of 5 is approximately 125.23, and I'm not actually sure in this case if it tells us I know it's in grams. We're just going to go with grams. Yeah, that'll be good enough. Part D is going to ask us, how long will it take for the population to reach 140 grams? Well, since they're asking the question how long, we're going to ultimately end up solving the equation for t, and the 140 grams is the amount of grams, so that of course is going to get stuck in the left hand side here. 100 e to the 0.045 times t. All right, so now in order to solve this, we're going to solve it algebraically first. Okay, so that's ultimately the first thing we're going to do, is solve this algebraically. And here's how we do it. You have to isolate the exponential first, since the t is in the exponent. So we're going to divide both sides by 100. Dividing both sides by 100 is going to give us 1.4 equals e to the 0.045 times t. The only way to get that variable out of the exponent is to rewrite this in terms of logs. So this is where taking the log of both sides, specifically a natural log of both sides, is going to be very convenient, because the natural log of 1.4, not something we're going to know easily, but the natural log of e to the 0.045t is going to be an important way to do this, because the natural log and e are inverse functions of each other, which means that the natural log of e raised to some power just gives you the power, the exponent. So we're going to get that the natural log of 1.4 equals 0.045t. Again, you're not canceling out the natural log and the e. That's not what's happening. You're taking the natural log of e raised to a power, which ultimately gives you 0.045t. It gives you the power. Another way you could think about it is you could bring that 0.045t out to the front of that natural log, and the natural log of e itself is actually the value of 1. So then you would get 0.045t times 1, which is still just 0.045t. And now to solve for t, you're going to divide both sides by 0.045. So t is going to equal the natural log of 1.4 divided by 0.045. That technically is the exact answer. Doesn't really do very much for us as far as indicating, a time that we can all understand. So once again, we're going to pull out the calculator, and we're going to plug this in. So it's the natural log of 1.4. Now you do need to make sure you do this, otherwise your answer will be wrong. You got to close that parentheses there, because you're taking the natural log of 1.4, and then you're going to divide that whole answer by 0.045. And we get 7.47 or 7.48 as an approximate value. And that was in days. All right, so I think we'll do that. We could do a whole bunch of other variations of this, but that's pretty much the idea behind doing an exponential growth problem like that one. Let's do one. What example are we on? Just number 2, right? Yeah, example number 2. Let's do one where we have to set up the equation. Now, I'm not going to run through necessarily all the steps after we get the setup, but we'll at least get most of the information set up, and then after that it's kind of calculator work or algebraic work, which you guys can do. So let's say that we've got a bacteria which is going to grow according to natural growth. Some of the books, by the way, call it uninhibited growth, meaning that there's no limit to how much something can grow. This is typically just called natural growth, from what I remember. But all right, so let's say that for part A, we're just going to say n is the number of cells and t is the time in hours. So n is the number of cells and t is the time in hours. So all we want to do is express n as a function of t. The problem is we're missing some information, but we can at least write the general formula, which we know should be n of t. There's your n as a function of t. And since it is going to be natural growth, it is going to be c e to the kt. In order to solve one of these problems, in order to actually do some work with one of these problems, you are basically going to always need to have the c value and the k value. You need some initial amount, and you need the growth rate in order to do this. So they have to give you some additional information, which I am about to do for part B. So part B says, if we know that the number of bacteria doubles in 3 hours, find a function that's going to express that. Write the function n of t. All right, so what we know is that the number of bacteria doubles in 3 hours. So what that kind of gives us, it doesn't actually give us a C value, but what it does give us is it gives us a way to find K, and that's important. So here's kind of what you have to think about doing. And then again, there's multiple ways of doing this. Once you kind of get the hang of this, it hopefully will make sense. We can let C in this case be anything that we want to. So let's just pick a nice easy number to deal with, and let's let C be like, I don't know, 10. Let's just say it's 10. We don't really know. We'll have e to the kt. But they do tell us something about that, what we need to know. They tell us that in 3 hours, well, there's your t value, the number of bacteria doubles, which means on the left-hand side, since the 10 doubles, it should now be 20. Well, now we can actually solve that for k. What we would do is we would isolate the exponential by dividing by 10 on both sides, and that gives us 2 equals e to the 3k. So what you should notice is on the left-hand side of the equation, what I got was a 2. That's not coincidental because of the fact that they're telling us that the bacteria doubles. And what you should notice is that there's no C value anymore. So if it asks you to find something where it triples, what you should get on the left-hand side is a 3, and your C value is gone. If it says it quadruples, you should have a 4, and so on. You should hopefully be able to start figuring that out. But now we can solve for k. Once again, we have to get it out of the exponential, so we will take the natural log of both sides of the equation. And then the right side, left side stays the same. The right side becomes 3k, which means that solving for k, it is the natural log of 2 divided by 3. You could also write that as 1/3 of the natural log of 2, which would be perfectly acceptable. If it asks you for some kind of a decimal approximation, you'll plug that in the calculator. I'm not going to pull the calculator back out for this. I've already done that part. It's approximately 0.23105. Now, if you are going to use a decimal, you need to use a bunch of decimals, because if you round these decimals for k as you go, if you round it to 2 spaces, the accuracy at the end won't be very long if you have to do more work with it. All right, so now if you wanted to know how long it was going to take to triple, well, then you know the left-hand side would be 3, and then you would actually solve for t in this case. So again, I'm not going to do the problem out, but like if part C said, how long is this thing going to take to triple? Well, that means that the left-hand side would be 3. I now know that the k value is the natural log of 2 divided by 3, and then times t. Now you could solve that for t. Again, I'm not doing that. You would take the natural log on both sides, solve it for t, and that would be how you would do it. All right, so both of those two things have been indicators of exponential growth. If you want something to have exponential decay, the main thing that's going to happen is that your k value is going to be negative, because positive growth, k is positive. Negative growth or decay is going to be negative. So growth, let's go with green here, growth, k is greater than 0. Decay, k will be less than 0. If k is 0, then ultimately you just have a linear function. It doesn't work. So growth, k will be greater than 0. Decay, k will be less than 0. And it's pretty much the same exact idea. This is typically used a lot of times in what is called half-life. That is something that you would see in more of an environmental science type of equation, something where you've got decay of, like I said, some kind of an element or something like that. But the general concept behind something like that is, say we have, once again, we have our y equals c e to the kt, and you're trying to find the half-life of something, which would be how long it takes for a certain element to decay to half of its current amount. Then what you would ultimately get on the left-hand side is a half equals e to the kt, and you would have to know how many years it took to get to, or how many days or whatever it took to get to that 1/2. You would replace that value for t, find K, you could find your decay rate in this case instead of a growth rate. There are some other really good examples of how this stuff works. Newton's law of cooling is something that I am actually going to leave out of this particular curriculum. If you take calculus, and this would probably be calculus 2 when you would probably see Newton's law of cooling, assuming that your instructor were to teach it. It's a really neat thing. Actually works for heating as well. But I'm going to leave that one out of here because it's something that could be developed by your calculus instructors. The last thing we're going to talk about for our examples is something which is not going to be what's considered uninhibited growth. It's going to be what is called logistic growth. So let me go ahead and create a new line here. Logistic growth. Or technically decay, but we're going to pretty much focus on logistic growth. So what's going to ultimately happen with something which grows logistically? It's going to look like it's exponential early on. So it'll start with an exponential type of growth. And then as it starts to grow, it's going to actually start to level itself off. And it's going to actually approach some value up here. It's going to get close to that value, which it'll never actually reach. And that value, and again, every book is slightly different. I use the letter M, capital M. That capital M is what is called the carrying capacity. Carrying capacity. And basically what that carrying capacity means is that's the amount that something can sustain in the long run. There's a lot more that goes into this, but the idea is something will grow really quickly, but then because you've got some kind of a limited resource, whether it's space or whether it's food or oxygen or whatever the different the things that it needs to be sustainable is necessary, it's gonna limit itself. So something's gonna grow really quickly and then it's gonna level off because you're running out of resources. That's the general concept behind a logistic growth model. When I teach calculus myself, I love to actually develop this. It's not something that we can develop now because we don't have the methods, but the formula for that is that your population is going to be that growth rate, M, divided by 1 plus A e to the negative kt. All right, and the reason that I use an A down there is because a lot of people, if I use C, people think that's an initial condition. A itself is not an initial condition, but you use the initial conditions to find the value of A. K still has to do with your growth rate. Notice, however, because it is a negative K down there, doesn't mean you're always going to have a negative growth rate. It just means that whatever your growth rate is, it gets multiplied by a negative value. T is still time. So M is your carrying capacity. In some fashion, it's got to tell you what the carrying capacity is. A is going to be found by taking that carrying capacity, subtracting your initial population, P sub 0, and dividing by that initial population. That is actually how you find the A value. Now, if it happens to be given to you, even better, but that's what that is. So the example that I'm going to use is a fruit fly population. Don't ask me why, it's just something that I found in a book. And this will be the last example for this, by the way. Fruit fly population. So we're going to have that P of T is defined to be 230 divided by 1 plus 56.5 e to the negative 0.37 t. All right, so just looking at this, there's a couple of things that you should be able to figure out pretty quickly. Letter A, what's the carrying capacity? And again, just looking at this, you should know that based upon our formula, the carrying capacity is the numerator number. So the carrying capacity is 230. And basically what that means is that 230, I guess, fruit flies is the maximum amount of fruit flies this thing can sustain over the long haul. um, I don't know, think about it like, I don't know, you've got fruit flies hovering around a banana or something like that. Eventually, the banana itself is going to run out. So 230 fruit flies is about all you're going to be able to keep around there. I don't know. That's a horrible example, but get the idea, hopefully. All right, and the second part is we're going to determine the initial population. Well, if you want to determine the initial or the starting population, basically you want your time to be 0. Okay, so we're just going to literally plug in 0 for the time. So initial population is P of 0 equals 230 over 1 plus 56.5 e to the, and what would be 0 power, because you're going to multiply the negative 0.37 times 0. Well, e to the 0 is 1, so what we get is 230 over 1 plus 56.5, or 230 over 57.5, which then you could plug into a calculator to get some kind of an approximation for that. And as a matter of fact, I believe this actually works out to be very nice. Pretty sure 230 over 57.5 actually works out to be 4. If I did that math correctly, I think I did. Okay. So your initial population is 4. If you simply want to know what the population is after 5 days, you would just plug in 5. Okay, I'm not going to go through the whole thing of writing all that out by plugging the 5 in for the t, but when you do plug 5 in for t, this one works out to be an approximation of 23 fruit flies after 5 days. And then if you want to know how long does it take for the population to reach a certain amount, you're solving for t. Oops, that should be in blue. How long does it take to reach 180 fruit flies? Well, considering we hit 23 fruit flies after 5 days, it should definitely take more than 5 days. So if you want to figure this one out, you're going to take 180, set it equal to 230 over 1 plus 56.5 e to the, what the heck was the k value there? Negative 0.37 times t. And that is definitely something that you could utilize a calculator for. Once again, if you had to solve this by hand, you would have to isolate that t. So you'd have to do a little bit of algebraic manipulation there, multiplying both sides by the denominator, or you could reciprocate both sides. I think we're going to go ahead and utilize our calculator in this case. It gives me a chance to show you one more cool thing on your calculator if you've never used it before. All right, so we're going to go ahead and go to the y equals screen, clear out what we had in there. Okay, so we have 180, that's one side. Okay, so if you've never used this next feature, this is pretty cool. Assuming that you have a TI-84 Plus, you can do this. We're going to make the fraction look like an actual fraction instead of just using the division sign. Makes it a lot easier without having to utilize all the extra parentheses. So we're going to push alpha, which is the green button, and then y equals. And what that brings up is the n/d as your first choice. So we're going to hit that one. And you can actually type a fraction in to look like a fraction. So the numerator will be 230. Scroll down to the denominator, which will be 1 plus 56.5 e to the negative 0.37. And instead of t, we're just going to use x. The variable does not matter all that much. And enter. And now we've got our two functions. So we're going to go ahead and graph these. Pretty sure if I start off with a zoom 6, I'm not going to be able to see what I need, but I'm going to start off with it anyway. Should make sense that we're really not going to see the intersection because it's supposed to intersect with the horizontal line y equals 180, which is way off the screen because I got a 10 by 10 window. So let's change our y values. Let's go to the window. And we're going to change our y maximum. It's got to be bigger than 180, so let's go up to like 200 and graph it and see where we're at. Sometimes you just got to keep playing with this, by the way, until you can find what you're looking for. So there's the exponential. And why am I not seeing the horizontal line? Okay, y equals 180, so what was my window? The y maximum is only 20. I meant to push 200. I missed a 0. That's what happened. Now, there we go. There's the horizontal line, and here comes the exponential. And I'm not going to be able to see the intersection because it's off the screen, which means I have to increase the x values. So let's go back to the window. Let's go to the x maximum and change it to 20. And graph. Hopefully this will work. And there's the intersection. Good. So now we're going to find the intersection, second trace, intersect. Yes, that is the first curve. Yes, that is the second curve. Let it guess because I think there's only one intersection. And boom, there it is. So it should take approximately 14.36 days or 14.37 days. So t equals 14.37 days in order for you to have 100 fruit flies. All right, I think that is that's probably pretty good for this video. Again, we're approaching a 40-minute video. I hate that it's taking that long, but these are not exactly short. And as always, should you need to watch any of these again or see something again, it's on YouTube, so you can go back and look at it. Or if you don't need some of the information, like I'm good with this, I don't need this video, then don't watch the whole thing. Only watch the parts that you need. All right, that takes care of our first unit.